Oh, it's kind of crowded.
Yeah.
Now put these right in front of me.
I'm confused about what day of the week it is.
Friday.
Feels like a Wednesday though.
Because of
Coffee hour. Is it?
Shrunk.
Can I change it here?
I mean, somehow. Can you change the resolution?
Turns it off.
Somehow this doesn't seem right. Can you make it 1024 by 768?
I'm not sure that's available on this, but
It should be there.
if this is plugged in, I guess. I think I probably
Oh, yeah.
plug
see
this
that-
in.
No.
Oh, it's there. Oh.
Now try it.
Is it better? And this is this screen.
Better.
I think so, yeah.
Does it feel warm in here? Or is it just me because I ran over here?
Yeah.
It was very
It was
possible.
warm and we opened the window.
Oh, you did open
Got
it, okay.
cold, a little
Yeah, it is a
cold.
little warm. Is that what you're saying?
Yeah.
Yeah.
But if you open the window,
It may need to be
Are they-
moderated
Yeah, I think-
again.
see Allen Hall, we all know and love.
Yeah, say goodbye to it.
With windows that open,
Months.
yeah, you'll just be locked in your cubicles 6 months, or 3 years from now.
Okay, so are we, I think we're ready?
What's NRL?
Naval Research Lab.
So they plan to use flying qubits as weapons?
Well, actually, right now, they're not too much interested in quantum computing, but Dr. Hilbert.
They should be.
Well, at least nobody's in his group is working on it very much.
They can't let certain other navies in the world get too far ahead. All right?
That's right.
That's true.
Okay, well, why don't we get started? So it's a pleasure to be able to introduce Vanita Srinivasa, who will be defending her thesis. Title is Designer Quantum Materials.
Thank you very much, and thank you all for coming. So I'll describe two classes of spin-based designer quantum materials. And the first one involves exchange-coupled spins. And I'll talk about how domain walls in Heisenberg spin systems can produce localized qubits, and how these qubits can act as flying spin qubits, as well as generate Einstein-Podolsky-Rosen pairs, and how we can tune the interactions between pairs of these qubits. The second class of designer quantum materials involves the spin-orbit interaction, and in this context, I'll describe spin-orbit superlattice quantum wires, and how these systems can be used to carry out spin resonance in space, as well as how we can encode single qubit gates in the band structure of the superlattice. So the concept of designer quantum materials is a broad one, but to focus our efforts, we concentrate on the theoretical design of quantum materials that are relevant for building a quantum information processor. And so the physical realization of information processing that's based on the laws of quantum mechanics involves several challenges, and a well-known set of requirements has been established by DiVincenzo. And the criteria that relate to quantum computation involve not only having well-defined qubits, or quantum bits, so that both their internal Hamiltonian and external interactions are well known, but also being able to have scalability so that many qubits can be incorporated into the system. We also need to be able to initialize these qubits to some reference state, perform manipulations or quantum gate operations that are much faster than the characteristic timescale over which the quantum information stored in the qubits decays, which can happen if the qubits interact with their environment. And we need to be able to read out the final result by measuring the qubits. So in addition to these requirements for local quantum computation, we also need to have a way of transporting quantum information. And if we want to perform quantum gates between spatially separated qubits, for example. And so this means that we need to be able to efficiently convert between stationary and flying or moving qubits, as well as having a way of reliably transporting the flying qubits from one location to another. And so we see that we already have several possible goals for the construction of designer quantum materials in this system, in this context. And so now we can look at the basic building block that we use, and that is a single spin 1/2 object, which is a two-level quantum system. And this system is described by a two-dimensional Hilbert space that's spanned by two states, and we can choose these states to be the spin up and spin down states associated with a particular component of spin. And these two states define a qubit. And in fact, in this case, the spin and qubit spaces are completely equivalent, since there are no extra states. So as a concrete example of a single spin qubit, we can think of an electron spin. And so the most general state of a single qubit can be written as a linear superposition of the basis states. And if we write that superposition like this, using angular spherical coordinates, then we can visualize this single qubit state as a vector on a sphere. And this is known as the block sphere picture, and it's a three-dimensional representation of a single qubit state in which the basis states are at the poles along the vertical axis. So in order for these single spin qubits to be useful, we need to have ways of manipulating them. And in particular, we'd like to find a universal set of quantum gates, meaning that any quantum gate can be constructed from gates in this set. And one way to do this is to have ways of performing arbitrary single qubit gates and a gate that can entangle two qubits. And so for single localized spin qubits, we can perform single qubit rotations using the Zeeman interaction, which is the coupling of spin to an external magnetic field. And depending on the direction of the applied field, we can generate unitary transformations around different axes of the block sphere. So in order to entangle two spins, we can use the Heisenberg or isotropic exchange interaction, which is of this form, where J represents the interaction strength. And depending on the time integral of J, we can generate different unitary transformations, which can be either entangling or non-entangling. And so if the time integral of J, for example, is equal to pi, then we get the operation which swaps the states of the two spins. So the idea of designer quantum materials is based on the fact that while a single spin 1/2 particle acts as a natural qubit for quantum computing, we can also think of it as an elementary building block that we can use along with its interactions in order to construct larger quantum systems which have properties that don't exist for individual spins. So for example, we can use several spins to define single qubits in which the internal interactions are an extra resource. And even with two spins, the exchange interaction that already exists between them can rotate the qubit from one basis state to the other without external magnetic fields. And if we construct a larger system of exchange-coupled spins, we can define a spin cluster qubit using the lowest energy levels of the system. So we can now go further with the idea of designer quantum materials and use spins to effectively construct a quantum field, and by tailoring the overall form of the exchange constant so that there's a domain wall separating the two possible patterns of dimerization, we can produce a spatially localized spin qubit. And by moving the domain wall through the system, this state acts as a flying spin qubit. So to look at the features of designer quantum materials based on exchange interactions, we can initially consider the exchange between just two spins. And so the Heisenberg exchange interaction commutes with both the square of the total spin and the total z component of spin. And so we can classify the eigenstates according to the quantum numbers associated with these operators. And the ground state of the system depends on the sign of the exchange interaction strength J. So that if J is positive, then the exchange is antiferromagnetic, which corresponds to antiparallel alignment of neighboring spins. And the ground state in this case has the minimum total spin of 0, and it's the singlet state. On the other hand, if J is negative, then we have ferromagnetic exchange, and in this case, the ground state has the maximum possible total spin of 1, and it consists of the 3 triplet states. And in both cases, the energy splitting is given by the magnitude of J. And here you can see that the spectrum for the ferromagnetic exchange is essentially the inverse of the spectrum for the antiferromagnetic case. So also, this singlet state and this particular triplet state are examples of Einstein-Podolsky-Rosen, or EPR pairs, which are entangled states. So now we can look at an open chain of spins coupled by a spatially uniform antiferromagnetic exchange, which is described by this Hamiltonian, and we can again classify the eigenstates according to the total spin and the total z component of spin. And if we look at the energy spectrum for a one-dimensional chain of an odd number of spins, then we find a twofold degenerate ground state with a minimum possible total spin of 1/2. And so we can think of these states as spin up and spin down states like those of a single spin 1/2 particle. And
I had a question.
yeah,
So in addition to Heisenberg interactions, you could have dipole-dipole interactions as well, right?
right.
Are you assuming something about the energy scales of various things here, that you are neglecting those terms?
Yeah, so we're assuming that so you're saying that the dipole interactions might also play a role.
Yeah, you have spins.
Right.
You have 2 spins, and all you have taken so far is just the exchange term.
Right, so we're assuming that the exchange is the dominant term in the
Okay.
system.
So they're far separated
Right,
relative to.
Typically is.
Okay.
right. So exchange is a large interaction also. So it's okay. Whoops. Sorry. Okay, so if we instead look, we can define a spin cluster qubit and an energetically stable spin cluster qubit using these two spin up and spin down states. But if we instead look at the case of an even number of spins, then we find a non-degenerate ground state with total spin 0, and so we can't define a spin cluster qubit in this case. But notice that the low energy part of this spectrum consists of a singlet ground state and a triplet first excited state. And so while we see that while the chain with an odd number of spins is analogous to a single spin, the chain with an even number of spins is similar to 2 spins. So in general, the basis states of a spin cluster qubit are superpositions of many, many product states. And here you can see an example of the qubit basis states for a 9-spin chain. So it's not very convenient to work with the full expressions for these basis states. But we can visualize the states of the qubits if we look at the spin density, which we define as the expectation value of the z component of spin at each site in the chain for these states. And here you can see that the qubit is effectively distributed over a one-dimensional lattice. And so there's an extra spatial degree of freedom that doesn't exist for single spin qubits. So now we can look at how we can produce flying spin qubits. So we've mentioned that the DiVincenzo criteria for implementing quantum information processing within a physical system include not only having well-defined qubits and quantum gates, but also being able to efficiently convert between stationary and flying qubits, as well as having a way of transporting the flying qubits without a significant loss of quantum information. So several different approaches to this problem have been explored, and one of the most common ones is to use photons, which can carry qubits in their polarization states, for example. We can also use multiple swap operations between nearest neighbor qubits within a long chain, but we accumulate errors with each non-ideal swap that we perform. So to see the problem with this multiple swap method, we can consider what happens during a non-ideal swap. So for 2 spins, the swap operation we know is generated by the Heisenberg exchange interaction when the time integral of the exchange is equal to pi. But suppose that we now have a small error, delta, in each swap, so that the state of the qubit is not completely swapped to the next site in the chain. Then as we keep repeating this non-ideal swap operation, we gradually lose the quantum information. And so you can see that this becomes a problem for long-range transport. In addition, the error threshold for quantum error correction for this method, which tells us how many errors we can have for a certain number of gates, is very relatively low for this method. It's of the order of 10 to the minus 7. And so we see that this is not really an ideal method for transporting quantum information over long distances. So another method for transporting qubits is quantum teleportation, which makes use of EPR pairs. But if we want to carry out both quantum computation and quantum information transfer within a single solid-state system, we can use chains of exchange-coupled spins. And the proposals which make use of this method typically involve transporting a qubit that's encoded in one or a few spins by allowing it to evolve from one end of the chain to the other. But in order to achieve high fidelity, you generally need very precise values of the exchange constants. So the systems that we consider are chains of spins coupled by nearest neighbor Heisenberg exchange interactions, which are described by this Hamiltonian, and we took the exchange to be antiferromagnetic. In particular, we considered these types of systems where the exchange coupling is dimerized, so that it alternates between two values, except at the center where there's a kink or a domain wall that forms the boundary between the two possible patterns of dimerization. And so the ground state of this system has a total spin of 1/2, and it consists of spin up and spin down states like a spin cluster qubit. And in order to, we here focus on the spin up subspace, but we can find completely analogous results for the spin down subspace. And so in order to visualize the ground state, yes?
So the spin swap method for reading out qubits,
Right.
do people consider that as a method?
For transport.
People,
Transporting?
yeah, so people do consider it as a method for single.
How do they implement the